So welcome to the second lecture of module 5. So in the last lecture, that was the first lecture regarding AC bridges, we have seen the general standard equations. So it was summarized that for AC bridges, we are having two standard equations, one for magnitude and other for phase, or one for real or the other for imaginary. So there are two standard equations for two standard balance equations for AC bridges. And then we have seen the general form of an AC bridge, and we have seen the how we apply the standard equations and all those things in the last lecture. And one more, we have seen the Maxwell's inductance bridge, where we have calculated the unknown inductance using Maxwell's inductance bridge. So today we will see another form of Maxwell's inductance bridge, that is Maxwell's capacitance bridge. Maxwell's inductance-capacitance bridge is also known as Maxwell's inductance-capacitance bridge. So in Maxwell's inductance bridge, R2 and L2 were the known quantities, and you got two independent equations so that you can get the value for L1, that is the unknown inductance. So we are calculating the unknown inductance in terms of non-resistance and non-inductance. That was the speciality of Maxwell's inductance bridge, and the variable resistance used was decayed resistance box. Last time I made a mistake. Decayed resistance box, the resistance value changes in multiples of 10 rather than multiples of 100. So it is multiples of 10 by which the resistance varies. And today we'll see the Maxwell's inductance capacitance bridge. So here the only difference is that the inductance, the unknown inductance, is calculated in terms of a non-capacitance. So there it was in terms of non-inductance, here it is in terms of a non-capacitance, or the unknown inductance is being compared with a non-capacitance. So these are the terms which we have to know. That is L1, the unknown inductance, and it has its own effective resistance R1, and the R3, R4, and R4, R2, R3, and R4 are the non-inductive resistances, and the C4 is, this was the one which I was talking about, that the C4 is a variable standard capacitance. So we will be using a decayed capacitor box as C4. So this is the bridge. So unknown inductance which we have to determine, then R2, R3, R2, R3, and R4, three non-inductive resistances, and then we have the variable capacitance here, that is a decayed capacitor box here. So here we'll first move on to the that is, if the bridge is balanced, then B and D should be at the same potential, that is E1 will be equal to E2 and E3 will be equal to E4. Keeping that in mind, we will move on to the Phasor diagram. That is, here you can see that I am taking I1 as my reference. So the resistive drop, that is I1 R1, is all along I1, that is I1 R1, and and one more thing, I1 is flowing through, the same current is flowing through R3 also, so that is here, that is I1 R3, which is also equal to E4. So under balance condition, E3 should be equal to E4. So that is here, that is all along I1. And what is E4? E4 is nothing but the capacitive current, divided by capacitive current multiplied by XC, that is omega, that is 1 by omega C4, and that is the voltage drop across this reactance, and that should also be equal to the voltage drop across this resistance, that is given by IR multiplied by IR4. That is, IR is the current flowing through R4, so that drop IR into R4 is nothing but E4, which is also equal to the capacitive current multiplied by the reactance of this capacitor, that is IC multiplied by XC. XC is nothing but 1 by omega C4. So that is here. Now I1 also flows through the inductance. So the inductive drop, that is I1 multiplied by omega L1, leads the current I1. For inductance, the current lags the voltage. So the drop across inductance I1 omega L1 leads the current I1, by an angle 90 degree. So if I take the resultant, this will be my resultant, and that is equal to what? E1, which is equal to E2, which is equal to I2 R2. So this length is equal to E1 as well as E2. What is E2? E2 is nothing but simply R2 I2. So we can see that this R2 I2 R2 is all along the length of I2. So what is I2? I2 is actually, so this is the I2 current. This I2 current splits into two parts, that is IR and IC. So I2 is nothing but the vector sum of IR and IC. So it's not the algebraic sum, it's a vector sum. So IR is all along this one. So naturally the capacitive current will be leading this current IR by 90 degrees. So the effective current will be, the resultant current will be I2. So this is I2, and the drop E2 is nothing but I2 R2 is all along the vector I2. So now what is this E? This E is nothing but the phasor sum of, or the vector sum of, E1 and E3 or E2 and E4. So we have determined all the voltages, that is E1 equal to E2 here and E4 is equal to E3 here. So this is E3 or E4. So I draw a parallel line like this. Now what is E1 equal to E2? This is my E1 is equal to E2. I draw a parallel line like this. So drawing the principal diagram for this parallelogram, I'll get the effective supply voltage E. So this is the phasor diagram under balanced conditions. Now I think it's very clear. Now if you go back to the calculation, we know that the basic equation, that is Z1 multiplied by Z4 is equal to Z2 multiplied by Z3. So Z2 is nothing but R2 and Z3 is nothing but R3 here, and Z1 is actually the series combination of resistance and inductance having an impedance of or reactance of j omega L1. So R1 plus j omega L1 multiplied by the parallel combination of resistance R4 and C4. So this is the resultant. So this is my balance equation. If I open it and group all the real terms and imaginary terms and equate the real parts and the imaginary terms separately, then I'll get, I should get the two equations for the unknown quantities, that is R1 and L1, which is these two equations, that is R1 is equal to R2 R3 by R4 and L1 is equal to R2 R3 by C4. So here we see that we have chosen R4 and C4 as the variable quantities. So these are the two independent equations. Why it is called independent equation? Because R4 is a term which is only present in this equation. We don't have R4 term here, and C4 is a term which is only in the second equation, and we don't find C4 in the first equation. So these are two independent equations. So variation of R4 doesn't affect L1 and variation of C4 does not affect R1. So this is the advantage of this method, and the previous bridge also had this this advantage. And one more advantage is that we can find the quality factor or Q factor of the inductance or the coil. That is, it is nothing but XL by R. So XL is nothing but omega L1, the inductance 1 that we are determined. Then that is R is nothing but R1. So omega L1 by R1 is the quality factor of the unknown inductance, unknown coil. And if I substitute for L1 from this equation, and if I substitute for R1 from this equation, I'll get, that is omega C4 R4. So we are getting the quality factor in terms of the two variable quantities, where omega is dependent on frequency, or omega is the angular frequency. Now one advantage is that, see, if you choose the resistances of R2 and R3 in such a way that if I calculate L1, which is equal to, so if I take the product of R2 and R3, then if I get in terms in order of 10 raised to 6, suppose L1 is equal to some value multiplied by 10 raised to 6 C4. Maybe it can be 2 or 3, any value multiplied by 10 raised to 6 C4. So an order of 10 raised to 6 multiplied by C4 results in L1. So that means that if you can select a capacitor value in microfarad value. So your decade capacitance box will be variation from 1 microfarad, 10 microfarad, 100 microfarad, then 1000 microfarad, like that. So you can easily select capacitor values in microfarad range. And so if you select the capacitor value in microfarad range, these two will result in an order of 10 raised to 6. So 10 raised to 6 multiplied by 10 raised to minus 6 will get an inductance value directly in Henry. So that is one of the advantage. And the major disadvantage of this method is that it is using a decayed variable capacitance box, which is which is bit difficult to in availability. That is why that is a major disadvantage. And then we will move on to the next one, that is shearing bridge. So shearing bridge is nothing but another bridge. So the previous two bridges were to find the unknown inductance. So this bridge is used to find the unknown capacitor. So C1 is the unknown capacitor, and C1 will have its own series resistance. So this resistance will indicate the loss, or will actually result in the loss in the capacitor. So this R1 represents the loss in the capacitor C1, and C2 C2 is another standard capacitor. So standard capacitors are either made of air or gas, and they are loss free. And C4 is like the previous one, a variable decayed capacitor box, and R3 and R4 are two non-inductive non-resistances. So R4 is connected parallel to C4. Now we'll see the bridge. So this is the bridge. So only difference is that this remains same when we compare with the previous circuit. This one will remain the same, and this one will remain the same, and this one is nothing but the unknown capacitor value that we have to determine. And instead of a resistance R2, we have C2. Now here also, if you see the Phasor diagram, if you take the I1 as the reference value, then you can say that that is this one. This one is nothing but this small R1. There is a small mistake in the literature. That is R1. So small drop in this resistance is I1 R1, and this. And if you continue, what is E3? E3 is nothing but this resistance, the drop across this resistance. That is nothing but I1 multiplied by R3. So this is my E3. That is all along I1. So E3, as we know, it is equal to E4. What is E4? It is nothing but either the drop across this reactance or the drop across R1. That is IC by omega C4, which is equal to IR multiplied by R4. So this is E4 and E3. Now we have to determine what is E1 and E2. Now we have this I1 R1. So we have accounted for this drop. We have to account for this drop. So what is this drop? That is the drop, that the current through the capacitor will be leading the voltage. So this is the I1 is the current through the capacitor. So the drop will be lagging the current by an angle 90 degrees. So that drop is I1 by omega C1. So if I take the vector sum of I1 R1 and I1 by omega C1, I'll get this diagonal, which represents my E1, which is equal to E2 as well. So what is E2? E2 is nothing but I2 multiplied by the reactance, that is 1 by omega C2. So that is also here. So we have E3 equal to E4 here, and E1 equal to E2 here. So parallel to this one, I draw this one, and parallel to this one, I draw this one. So that this is my parallelogram, and if I consider the principal diagonal, I'll get the resultant voltage, that is the total voltage supplied by the supply. Now very simple, that is, if you know the basic equation, that is Z1 multiplied by Z4 is equal to Z2 Z3. If you substitute all the values, this is what we get, and group all the terms, that is real terms and imaginary terms, equate the real terms and imaginary terms separately. What you get is, that is R1 is equal to R3 C4 and C2, and C1 is equal to C2 R4 and R3. Again, you can see that R4 C4, these are two independent equations. C4 is only present in this term, and R4 is only present in this term. And one more thing we can identify is that the dissipation factor. Dissipation factor is dependent on the dissipation angle delta. Delta is nothing but the angle between this is the angle delta. That is the dissipation factor is the tan of this length divided by this length. That is the capacitive